Hello students, welcome to the 26th lecture on particle physics, and today we are going to start discussing neutrinos, the most elusive particle, the most abundant particles after the photons, but the least understood one. Though these neutrinos were first theoretically conjectured by Wolfgang Pauli in 1930 in order to save energy angular momentum conservation law. Then in 1933, Enrico Fermi gave his celebrated theory of beta decay, where neutrinos were an important ingredient, a particle. Therefore, Fermi accepted that neutrinos of Pauli should exist in nature. Then after that, people started trying to look for the neutrinos, and after 26 years of Pauli's hypothesis, in 1956, it was discovered by Rines and Covens in the experiment at nuclear reactors. And after that, these neutrinos have traveled a long way. And the importance of this field you can understand by realizing the fact that almost 10 Nobel Prizes have been awarded either directly where neutrinos research have played important role, or where these neutrinos have been observed, like in the atmospheric neutrino experiment, solar neutrino experiment, etc. Therefore, this field is quite fascinating, quite interesting, and as well as at the same time challenging. And going to start this, we will talk about the discovery and every other thing, what we have learned in the first series of lectures, that the neutrinos are fundamental particles of the standard model of particle physics. They exist in 3 different generations of lepton family, and there are antiparticles, and particles and antiparticles are different in the standard model of particle physics. Therefore, we have nu E, E minus as the first generation, nu mu, mu minus as the second generation, and nu tau and tau minus as the third generation lepton family. And then we have antiparticle corresponding to this, E plus nu E bar, mu plus nu mu bar, and tau plus nu tau bar. What are these neutrinos? They are weakly interacting particles. They do not participate in strong and electromagnetic interaction processes. They only participate in the weak interaction process. And if they are massless, they won't participate in gravitational interaction. But since standard model does not include gravitational interaction, therefore all the time we'll be talking about electromagnetic strong and weak interactions, and here in the case of neutrino sector we will only talk about the weak interaction processes. Then what we know, that they are fermions, they are spin half particles, they are neutral, they don't carry any charge, and they have been kept massless in the standard model. The other important thing which we have talked about in the last class, that neutrinos oscillate, it changes flavor. You start with a nu mu beam, it converts into nu E, or it gets converted into nu tau, or so on. Then there is a challenge to see that whether neutrinos, if oscillation exists, then that means neutrinos have got mass, and if they have got mass, then there are 2 possibilities. Either they can be Dirac neutrinos, or Majorana neutrinos. And if they are Majorana neutrinos, then we need theory beyond the standard model. Therefore, for us, neutrinos are Dirac neutrinos. Now, why we should study them? Because if there are no neutrinos, there will be no shine in the stars. Because as we know, stars are shining because of nuclear fusion reaction going on. Proton-proton burning is going on. Or in heavier stars, or during the death phase, whatever is happening, neutrinos are getting produced. And if there are no neutrinos, that means we are not talking about fusion reaction. And moreover, when we talk about our sun, then that means there will be no energy from sun to keep us warm. Now, if we don't talk about neutrinos, then we cannot understand the existence of elements higher than helium. We can understand the existence of hydrogen and major fraction of helium in the Big Bang nucleosynthesis. But beyond that, whether I'm talking about carbon, nitrogen, oxygen, calcium, iron, uranium, lead, etc., whatever you call it, if you look at the periodic table of the chemistry department, or from a chemist, if you look at the periodic table, then except for the transuranic elements which you artificially prepare in the lab, all the elements that we talk about, they have their sources in the stars that we will discuss, and their neutrinos have played a very important role. And that means if we are talking about there's no carbon, or there will be no oxygen, or that means there will be no water. That means what we are talking about, that the water H2O, the water we drink, we don't realize that from where this hydrogen and oxygen has come from. This hydrogen is the result of the Big Bang. That means this hydrogen atom is 13.6 billion years old. And this oxygen atom is from some remnant of stars. Therefore, there are millions and millions of oxygen atoms in the glass of water. And it's not that every glass would contain the same source of oxygen. Some oxygen will be from some stars, some another oxygen will be some other star, and so on. This means thousands of stars have contributed to existence of oxygen atom to have water in a bucket. And that means if there is no neutrino, there will be no earth, no moon, and that means no life. And that is why we must try to understand these particles. Though experimentally it is quite challenging, but since 1930s, efforts are going on to understand and unravel the mystery of this particle. Why we should understand it is because you can see that almost 400,000 billion neutrinos per second, they come from the sun. Then neutrinos are coming from nuclear power plants. Neutrinos are coming from the Earth's core. Neutrinos are coming from the other stars. Neutrinos are coming from supernova as and when they happen, and so on. Therefore, we are really living in sea of neutrinos. And more interesting, whether we talk about dates, tomato, banana, potato, dates, etc., etc., all of them have traces of elements that gives rise to neutrinos each second. For example, a single banana emits 1 million neutrinos per day. There are 700 million of neutrinos for every proton in the visible universe. And that is why we must try to understand this mysterious particle. This is what I was talking about, the periodic element from the chemistry department. As you can see that except for hydrogen and helium, majority of helium and almost all hydrogen, they have been produced during Big Bang nucleosynthesis, and that is why they are more than 13.6 or about 13.6 billion years old. But all the others that you see, the sources are exploding massive stars, exploding white dwarfs, dying low mass stars, merging neutron stars, etc., etc. And that is why all the gold we talk about, the coal we talk about, whatever you talk about, if neutrinos are not there, we won't be able to understand the existence of these elements. In fact, every star in this universe is an incredible neutrino factory throughout its lifetime, including our star, that is, I'm talking about sun. Therefore, without neutrinos, you cannot think of nuclear fusion reaction. Always, if there is a nuclear fusion reaction, neutrinos will be produced inside the sun, where proton burning is going on. And as we know that sun's lifetime is 9 billion years, that means in the current phase, sun will be there for 9 billion years. 4.5 billion years have gone, and it will be there for another 4.5 billion years. And all the time, the neutrinos which we are talking about, like the thumb, through this thumb, almost billions of neutrinos are passing through. And these neutrinos through this thumb, they are coming from the sun, they are coming from the other stars, they are coming from Earth's core, which are the sources of geoneutrinos. If they are coming from the nuclear power plants, they are coming from the cosmic rays through when protons interact with the Earth's atmosphere, we have pions and kaons, and those pions and kaons give rise to neutrinos. Therefore, trillions of neutrinos are passing through our body each second. And since their interaction cross sections are very small, therefore the chances are once in our lifetime of say 75, 80 years, one is going to interact with an atom of our body. And that is why you can realize that there are umpteen sources of neutrinos, and there are trillions of neutrinos constantly coming to us, whether it is day or it is night. Night, why I'm calling? Because sun, even if it is in USA and we have nights and there is day, those neutrinos travel all the earth to come to us without a single interaction inside the Earth's atom. And that means though sunlights are not coming to us in the night, but the neutrinos are coming to us. And that means all the year, throughout 365 days, round the clock, we are getting trillions of neutrinos. Those are passing through our body. And that is why it's important to understand this particle. Now, let me just go back to the basics that we have discussed in the second lecture on particle physics. And what I had talked about, that if I am talking about a radioactive nucleus, that decays at rest, then this nucleus will give rise to a daughter nucleus. And if there is only electron coming out from it, then if it is at rest, then Y and electron will be emitted exactly in the opposite direction to conserve momentum. And we have seen that if this is so, then the energy of the emitted electron will be the function of the masses of these fellows, X, Y, and the emitted electron. And that means energy of the outgoing electron will be unique, because this is function of the masses of the particles, and masses of the particles are fixed quantities. They are not going to change. And no matter whether you are talking about 10 electrons, 100 electrons, millions electrons in these decays, all the electrons should have unique energy. This is what I had plotted in our initial lectures, that if electrons energy is on the x-axis and number of emitted electrons we are plotting on the y-axis, then no matter how many electrons I am talking about, all will have unique energy, and that means this should be a discrete spectrum. The other important point was that this X, when was decaying into Y and electron is a spin half particle. While it was observed that these two guys, they have got integer spins. And when they have got integer angular momenta, since we know that angular momenta in any process should be conserved, integer and half cannot give you an integer, and that is why there was a crisis. Therefore, one crisis was the experimentalist observed a continuous spectrum, and another crisis that was telling us about the energy momentum conservation laws violation, and the other was telling us the violation of angular momentum conservation. Therefore, what we had the violation of energy momentum as well as the angular momentum. But the point was, the missing energy was very, very small, and till that point the particles which were known to us were proton, neutron, electron and photons. That is all. These were the particles known to us, and we cannot add this particle anywhere to this position, because this mass is 0.5 MeV, and this spin is again 1. This was not going to help us out. The masses here is 938, 938.2, 939.5 MeVs. Therefore, the missing energy was very tiny, and there was angular momentum conservation laws violation, and the energy spectrum was continuous. It took almost 17, 18 years to resolve this problem, and it was resolved by Wolfgang Pauli. Therefore, this was the observed spectrum, this was the discrete spectrum that we are talking about, and this red bar was expected from theory if this is a two-body decay, and this black continuous curve was the experimental observation. So therefore, to rescue this angular momentum and energy momentum conservation law, 1930, Pauli wrote a letter that was opened in a Tübingen's conference. He was not himself there. I have hit upon a desperate remedy to save the law of conservation of energy, namely the possibility that there exist in the nuclei electrically neutral particles that I call neutrons, because at that time Neutron was even not observed, the member of nucleus family or nucleon family. Only proton was there. Therefore, he called it to be a neutron. I agree that my remedy could seem incredible, but only the one who dare can win. Unfortunately, I cannot appear in person since I am indispensable at a ball here in Zurich. Now, the important point was he was suggesting a neutral particle, but I have not written the complete letter. He was also suggesting that this is very difficult to observe. And when you are proposing something in physics, and at the same time you are telling that you cannot observe it, then that means nobody will take you seriously. And this is what had happened in the Tübingen conference. But later, in the later years, he again presented it, and in one of the conference, Enrico Fermi was there, and he gave the then after a year celebrated theory of beta decay. From there, people started then believing that perhaps there could be neutrinos. And therefore, let us stop here. And in the next lecture, we are going to talk about uh, more about this elusive particle. That is what I am calling it as neutrino. This neutrino, the name was given by Enrico Fermi when he was developing Fermi theory of beta decay. Therefore, in 1933, this Pauli's neutron was rechristened to neutrino, and that is what we call today as neutrino. We will see in the next lecture that how for the first time neutrinos were detected and how they are being produced inside the core of the sun, and they play important role in physics. Let's stop here for today. Thank you very much.